So, in the last class what we did was that we showed that what the similarity transformation was and how it can predict the right result, right. At the same time we showed that the scaling was able to predict the correct variation. Okay. Now, we also suggested in that particular lecture that if it is just the value of the gradient at the wall, be it temperature, be it velocity, that is all that we need for evaluating what will be the heat transfer coefficient and the skin friction. Why resort to all these things? Let us devise something which is a little bit more simpler, right, and that is how we suggested that maybe we can have a semi analytical type of an approach. Okay. So, based on this we move to something called the integral solution. Okay. So, this was like von Karman and Paulhausen. Okay. So, the main building block of this particular approach is assume a velocity profile, okay, which is not exact because we do not know without the actual solution what the velocity profile would look like. Okay. So, assume a velocity profile for u and t basically, right, okay, inside the boundary layer, thermal or otherwise. Okay. And because this should work, because all we need to kind of be concerned are variables like these, right, at wall, right, that is our main concern. So, why not assume something for u, something for t such that, so that means if the profile is like this, right, the normal boundary layer is like that, correct, that is what we drew. So, if I can draw a inexact profile something like that, okay, which kind of resembles this, okay, but it does not quite, it is not exact because we do not know the form, but if this boundary profile whatever is the assumed profile, so to say, should obey all the boundary conditions, right. Okay. So, I cannot have a profile which is like this, say for example, okay, that will not be physical, okay, that will not for example agree with the boundary conditions either. So, one is that it should obey all the boundary conditions, and the second thing is that it has to be physical in the sense that it has to obey certain physical characteristics, like for example this profile that I drew over here, this curved kind of a wiggly pattern, right. You know that this profile is not physical, because why a profile should be like that, right, because the high velocity, low velocity, it cannot exist in a steady flow like this, okay, which is laminar in nature, correct. There is no mechanism by which why this should happen. So, even though this profile might satisfy the boundary conditions, this is not a physical profile. Okay. So, let us take this more carefully because I want you guys to get the, so this is the actual profile. Say for example, I draw a profile like this which kind of agrees with the boundary condition here, with the boundary condition there, correct, but in between it has got all these wiggles. Okay. So, this is not allowed, okay, since it is not physical, right. That is the most important part, that it has to make common sense, right, and there is no mechanism through which this flow will make something like this, okay, even though the boundaries are still satisfied. Okay. So, these are the two prime parameters that we need to get a feel of. One is that it has to obey the boundary conditions, second is that it has to obey the physics. Okay. Let us look at, before we do this, let us put down one particular form, okay, which is called the Leibniz formula. Okay. So, Leibniz formula for differentiation of an integral with respect to a parameter, okay, with respect to a parameter. Okay. So, we change the pen color to something like this. Okay. So, let us take this particular form, and this will come in very handy. This is the generalized form. Okay. So, pay attention to the details. Okay. So, that is the form. That is the first one, plus minus that is the Leibniz formula. So, you can see that how this will come in handy, we will see in a second, but this is the form of the Leibniz formula. Okay. Now, we are going to need this when we actually do this integral formulation. Okay. Now, let us take the case of a, let us go back to our problem, let us take the case of a flat plate. Okay. It can be a wedge also. The wedge part we will do the similarity a little later. Okay. So, flat plate will be like this, wedge will be something like that. That means an inclined flat plate, okay, whatever it is. Okay. So, let us take that particular form and let us try to work out the equations. Okay. So, this is the standard, this is the flow u infinity t infinity, this is x and y, this is the corresponding delta. The thermal analysis we will go a little later. Okay. So, the continuity equation is du dx plus dv dy is equal to 0, this is 1. Okay. The x momentum is du dx plus v du dy I will tell you the origin of the last term, this is 2. Okay. This origin of the last term is comes basically from the pressure gradient, right. This is basically nothing, comes from the Euler's equation, correct, outside the boundary layer. So, for a flat plate this is equal to 0, right, for a flat plate it is equal to 0 for flat plate, but when you are dealing with a plate which is inclined, okay, this will not be equal to 0, right. So, this is basically the variation of the free stream velocity with x, that is all that is, right, and that comes from the Euler's form. Okay. So, the boundary conditions we already know, y equal to 0, u equal to 0, v can be equal to 0, it can be also equal to some other quantity which is called blowing or suction. We will cover this a little later, but it is like if this plate is kind of porous, okay, that means there is a flow coming up like this, that can be accounted for by Vw, okay, or if the flow is porous and the fluid is actually seeping through, okay, so that can be given as Vw. Okay. So, it is normally will be 0 for impervious plate. We will do all these special cases later, I am just writing it in a common way, so that later on we can use we do not have to come back to the integral formulations once again. Okay. But most of these terms are 0, as I said this is 0, this is also equal to 0, okay. But there are special conditions, as I said, that in some cases there can be a flow, that is suction or blowing, right, or there can be this flow outside the boundary layer may actually vary. Okay. So, now what we do is that we take the continuity equation and we integrate it with respect to x. Oh, sorry, with respect to y, okay, because that is the y variation we are trying to take out. So, du dx dy plus 0 to delta dv dy into dy is equal to 0, right. Okay. So, that is the form that we have. This leads to 0 to delta du dx dy plus v delta minus v 0 is equal to 0. Very simple, right? That is the form. Now, we are going to apply Leibniz rule on this. Okay, we already established the Leibniz rule. Now, we are going to apply it first to our continuity equation. Okay. So, by Leibniz rule, this will be du dx dy will be u dy minus u at delta d delta by dx plus u 0 d 0 dx, right. Okay. That is the lower boundary, 0 is basically the lower boundary, right. So, this gives you du by dx 0 to delta u dy minus u infinity d delta by dx. Of course, this goes down to 0, the second the third term. Okay. So, therefore, now combining the full continuity equation, therefore, that is the full form that you get. Okay. Now, of course, v equal to v at 0, you can put whatever values that you want, v at delta you can put whatever values you want, okay, and all these things are incorporated. This is the most generic form of the equation that we can write, got it. Okay. So, now that we have taken care of continuity, let us move on to the momentum. Let us write the momentum equation in a conservative form. This basically goes to 0. I am putting the whole thing so that it is easier for one to understand that how we are proceeding throughout the problem, right. So, that is the whole form of the equation. Now, again integrate with respect to y. So, this will come as this. Got it? That is the full form. Okay. Now, again you can apply your Leibniz. Okay. I am not going to go through the steps, but you can apply your Leibniz accordingly. Okay. So, the form that you are going to get after Leibniz . Okay. Right, the full version of this full equation. Okay. So, you can see a few things over here, okay, which we can eliminate, okay, and some of those things should be pretty common sense as well, that what are the parameters that we can eliminate. Okay. So, let us see that which are the parameters that we can safely eliminate. Okay. If you take your pick, say for example, few things to note, what is u square at delta? That must be u infinity square, right. U at delta is actually equal to u infinity square, right. Similarly, this particular parameter obviously will go to 0, we know that for sure, right. U v, whatever is the nature of v, even if there is suction or blowing, u is equal to 0 always. So, that should go to 0 at the same time. Of course, this parameter will stay depending on what you want your u v to be, okay, and or will it stay, we will see to that in a little bit. Okay. And of course, on the other hand, if you go to this side of the equation, you will find that what about the nature of for this, should this go to 0 as well, because you are looking at the shear stress at the edge of the boundary layer, right, where the flow, the velocity should have actually become equal to u infinity. Okay. All that gradient is very small, that is what we are arguing. So, so therefore, we can write this equation in a more nicer form. This part remains the same, plus u infinity, if you take the u infinity, v is equal to actually u infinity. Okay. So, this is will be given as v 0 plus u infinity d infinity dx, okay, and d infinity dx minus dy is equal to u infinity delta into du infinity by dx, okay, minus gamma du dy evaluated at 0, right. So, that is the total expression that we get. Okay. So, now doing some more algebra, taking u infinity square out, 0 to delta u by u infinity square dy minus d by dx square 0 to delta u by u infinity dy is equal to minus u infinity, okay, minus v u infinity. This is whatever that Vw was, suction, blowing, it can be 0 also, okay, suction, blowing or 0. So, that is what we are arguing over here, okay, plus u infinity delta du infinity by dx minus tau wall by rho, okay, minus tau wall by rho. Okay. So, that would be the other part of that term. Okay. So, the tau wall minus rho is basically nothing but du by dy evaluated at the wall, right. So, this is the total expression that you get. Okay. And simplify this by a little bit. So, infinity u by u infinity dy plus got it. Now, so this is the total form of this equation. Now, in many cases you will find that this will go to 0, this will go to 0. So, that will be the form that we will be left with, okay, in the absence of any suction and blowing or in the absence of any free stream variation in the free stream velocity, right. Now, based on this we can define basically two parameters, one is called delta 1, which is basically this dy, this is has got a name, it is called the displacement thickness, may have heard about it in your fluid mechanics course, right. So, this is displacement thickness. The other one is basically what we call the momentum thickness. Okay. So, the displacement thickness and the momentum thickness. Okay. So, these are two parameters, one basically represents this, one basically represents that, right. Okay. Now, putting these two terms in, this is the global equation. Got it? So, this is the global equation, right. So, we have reduced the differential equation to an integral form. So far this particular equation is exact, there is no problem, okay. We have not assumed anything. So, if you take a differential equation, you can arrive at this form without much of an assumption. Whatever is the boundary layer assumption, that is still valid, except that we have not assumed any velocity profile as of now. Now we are going to do that, okay. So, let us assume a polynomial velocity profile, okay. Why a polynomial velocity profile? Because it should be able to satisfy the boundary conditions that are at hand, and a polynomial kind of can represent, okay, without any kink the boundary layer velocity profile, right. So, it can be other profiles also, by the way, so long as it makes physical sense. So, this is a common polynomial profile ABCD, okay, typical third order polynomial, okay. So, y is equal to 0 at u equal to 0, right, and y at y equal to delta u is equal to u infinity, at y equal to delta du by dy is equal to 0, right. These things we know, right, we already know these parameter space, okay. So, if we now try to put at y equal to 0 what happens, and for a flat plate, before we go to that, for a flat plate this this equation gets revised a little bit, because your V w is equal to 0 and du by dx is equal to 0 also, right, flat impervious plate, right. So, for these two plates this is added assumption can be done, okay. So, now the point is very simple, let us now derive that what will be the values of these coefficients, because that is what we need to plug in, right, okay. We need to plug in over there, okay. So, we need a fourth boundary condition, because there is A, B, C, D, right. So, we need one more boundary condition over here for V. So, for that particular case at y equal to 0, you are assuming that d square u dy square is equal to 0. This is called a derived boundary condition, okay. So, based on this let us work out the profile. So, from u equal to 0 leads to A equal to 0, right. U delta equal to u infinity leads to A plus B delta, of course A is being equal to 0, plus C delta square plus D delta cube, okay, D delta cube, that is u infinity, right. Du by dy at delta is equal to 0, okay. So, that would imply B plus 2C delta plus 3D delta square is equal to 0. Thirdly, dy square, okay, at 0 is equal to 0 implies 2C is equal to 0, okay. So, based on all these things, accumulating all these parameters, okay, we have u infinity is equal to B delta plus D delta cube, okay, got it, and the other one is 0 equal to B plus 3D delta square, right. Okay. So, you can solve for B and delta from these expressions. So, therefore, u by u infinity becomes 3 by 2 y by delta minus half y by delta cube. The velocity profile that we get, assuming that this is the parent equation. We have taken care of two of the terms, and this is the velocity profile that we have assumed, right. So, this is approximate, this is not approximate, that is exact. Okay. So, this is approximate and this is the velocity profile that we get, got it. Okay. So, for no suction and blowing particular case and for a flat plate, this is the equation. So, therefore, if we write tau wall by rho, that will be the form, right, of the expression. So, now if we put this thing together, this is basically what we wrote earlier, remember, u by u infinity dy plus du dy at y equal to 0. So, now you plug in all the parameters, as u infinity square 0 to delta 3 by 2 y over delta minus half y by delta cube, that is the first term. The second term is 1 minus 3 by 2 y over delta plus half y by delta cube, right, okay, into dy, that is equal to 3 by 2 u infinity by delta, right. So, now it becomes du by dx u infinity square 39 delta by 280 is equal to 3 gamma u infinity by 2 delta, or d delta square by dx equal to 280 by 13 gamma by u infinity, right. Okay. So, now it is very easy because delta only depends on x, that we already know. Okay. So, in this particular case, if you do this, you will get delta by x equal to 4.64 into Reynolds number x to the power of minus half. Cf will be given by tau wall by rho u infinity square, right. So, you see that by using this simple enough expression, okay, we have got this result which is 4.64, right. Remember, the exact solution gave us something like 5.2 if you recall the graph. So, we are not way off, we are off by about 10% or below in this particular case, right. So, that is what we get. Okay. So, just by using this approximate analysis, we got an answer which is pretty close to the actual value. So, this proves that the integral approximation is not a bad idea after all. Okay. So, based on this, what we have shown that your delta, you have to, after doing all these things, all we need is ultimately that expression for delta, right. Once we determine delta, everything, right, Cf and everything are basically dependent on delta, right. So, that is the thing that we have found out. Next class we are going to go and do the integral formulation for the energy equation. Thank you.